Hi, in this video, we're just going to talk about a couple of miscellaneous topics regarding the general linked list. So the first topic is the performance of linked list, and we'll compare that to the performance of array. With the operations that we're going to consider first, it would be the insertion and removal, which, as we know, just involves a couple of pointer changes. Once we know where to insert or where to remove, so insertion and removal is typically considered a very fast operation. So what about the same operation, but in an array whose elements are all stored in one contiguous block of memory? Well, to insert something in the middle of an array, like we're trying to insert number 9 here, well, we cannot just jam it in because there's simply no room for it. So we have to find a bigger piece of memory, and then we have to copy all the existing data from the original block of memory to this new block of memory, and copy the second half of this block, in one space over, so that we have room in the middle to insert the new data. And copying, especially copying a large block of data, can be very slow. So insertion is slow, and you can imagine for removal, we're shrinking the array, and we're also doing the copying. So that is also very slow. So insertion and removal for array can be very slow. So then you ask the question, then, okay, if linked list is fast, then why don't we use it all the time? Well, the problem is it's not fast for all operations. So like we said earlier here, that the linked list insertion and removal can be fast once we get to the right node. But to get to the right node in the linked list can be very slow. And that is because, as we saw in some the method that we wrote earlier, to get to the right node, we have to start from the head and visit node by node by node until we get to the right one. And the reason for that is, even though I kind of draw the picture here in a nice linear fashion, but inside the computer memory, because we are allocating each of these blocks at different times, they can be all over the place. So we have no choice but to just follow this chain when we try to find the right node. So that operation can be very slow. Now compare this with accessing an element in an array. Now remember, all the elements in an array are stored in one contiguous block of memory. That means each of the elements is at a fixed distance or fixed offset from the beginning of the array that can be very easily calculated. We just have to know how big each of the element is, right? And then just multiply by its index. So to get to any element in an array, then we just calculate the offset and jump right to it. We don't have to walk through all the elements preceding that element that we want to get to. So accessing an element in an array is a very fast operation compared to the same operation in the linked list. So here is a summary of what we just talked about. And as you can see, linked list and array, they both have their own advantages as well as disadvantages. And which one do you choose to use, kind of depending on, among other factors, which operation you expect to use the most. So for example, if your project is going to store data that requires frequent insertion and removal, then you probably want to use something like a linked list. So it all depends. And there are other considerations such as which one takes more memory. and that kind of things. And then there are some data structures that actually try to have it both ways, kind of combine the best of from both the linked list and arrays. But I'll leave that to a advanced data structure class. And another topic that I like to touch upon is mixing operations. Specifically, if we're in the middle of doing a list traversal, and then someone else comes in and insert or remove data from the list, it can actually cause problem. Why is that? Well, let's look at this particular example. We're doing a traversal, and let's say our current pointer is pointing at 66. Someone else comes in and remove 88. Well, then the next call to iterate, which is supposed to return the next number in the list, what should it do? Right? Should it return 88 or should it return 99? And what if the iterate, the way it was written, actually did not take into consideration that someone else can come in and do this kind of thing, yank things out from under its feet? Maybe it will even crash, right? So an analogy of mixing these operations would be, let's say we're reading a book. So we're flipping through the pages. That's kind of like a traversal, right? And then a magical or invisible hand would just rip some pages from the book. That's like removing things in the middle of a traversal. That hand might be even removing the page we are on right now, right? So mixing operations like this is generally undesirable. So it should the behavior should be well defined. It should either be handled uh, or it should be prevented altogether. And you might say, well, this is fairly obvious. Nobody would ever do this. But believe me, I'm speaking as someone who has done this plenty of times and wasted many hours scratching my head of what went wrong with my code. And lastly, I'll leave you with an optional exercise that you can try re-implementing the linked list, but without using the header node idea that we use in our implementation. So that would mean the head of the linked list would just point to a data node instead of a node. And you can try to rewrite some of the methods such as insert sorted and remove. And also, you should try to do direct manipulation of the next pointer. And that is without using the node.insert after and node.remove after methods. So just directly manipulate the next pointer in the nodes. And if you do that, please do make sure to handle the corner cases of inserting or removing the very first element and very last element. And if you do that, then you can compare and contrast this approach with the approach that we have taken. Then you can decide which approach you like better. As a point of reference, when I learned linked list, I learned the way that is suggested in this exercise.